Hello and welcome to this podcast for Radiation Physics for Wenatchee Valley College. I am Todd Bussey, your instructor, and I hope you find this podcast and all the other podcasts for this class helpful. The next piece that we have is we're going to go on to the electromagnetic spectrum just a little bit. And the picture that's on the screen is an electromagnetic wave. The red lines represent the electric field. The blue lines represent the magnetic field, the magnetic field based on magnets, and they are perpendicular to each other, and the thumb is pointing in the direction that this piece of light is going. And so we need to talk a little bit about waves and the wave theory of light, because there are two theories behind light, the wave theory of light and the particle theory of light. It's called the duality of light. And I'll have you read a little bit from the Nobel Physics Prize website so that you can get a little bit more information about the duality of light. But we have to talk about some properties of waves. One of the properties of waves is wavelength. And the wavelength is a distance between repeating units of a wave pattern. And we usually use the symbol lambda. It's basically an upside down Y is what it looks like. And wavelength is usually from crest to crest. There's a picture on that's up there, and so if we look at from crest to crest, how long that is, will be the wavelength, and it could be a meter, it could be times 10 to the negative 6 meters. It's going to be a length in there, so that will be wavelength, and all light has a certain wavelength. The next piece that we're looking to look at is frequency, and frequency is a number of cycles of repetitive waveform per second measured in hertz or cycles per second. Well, basically, it's a number of wave crests that go by in a given time period, and we talk about number of wave crests per second is what a hertz is. And frequency is dealing with pitch. So when we talk about the pitch of a sound, we're talking about the frequency of the sound. The higher the pitch, the higher the frequency. So that's the easiest way for me to think of frequency is when I talk about sound. The next piece of a wave that we're going to deal with is amplitude. Amplitude is the non-negative scalar measure of the wave's magnitude of oscillation. So basically we want to figure out how high is the wave. Now, is it a 3-foot wave? Is it a half a foot wave? Is it a centimeter wave from the equilibrium point, the center point? Because a wave goes up and down. So you can see from the picture that the right-hand side, the little y value, is the amplitude of that wave. However high that is in meters is what the wavelength of the amplitude of that wave is. Now, a piece that is idea that's related to frequency is called the period. The period of a wave is the time the full wave takes to pass a given point. So if we go from crest to crest, how long does it take from crest to crest for that wave to go by? And if you've thought about it a little bit, period and frequency are related to each other. Period has the notation of t, don't ask me why, but period is t, frequency is little f. So period and frequency are inverses of each other, are reciprocals of each other. So if we know what the period is, let's say 2 seconds, we know the frequency is a reciprocal of that, or 1/2. That means that it's going to be 1/2 a hertz. Half a cycle per second will go by in that time frame. So we have period, we have frequency, and they're reciprocals of each other. Now, these kind of all come together in the wave equation. And v on the wave equation is velocity. How fast is the wave going? We can calculate how fast the wave is going by looking at the frequency and the wavelength. So the frequency is cycles per second, and wavelength is meters. So if you remember velocity or speed, that's going to be meters per second. So when we take 1 over seconds times meters, we're going to get meters per second, or speed. And that will give us the speed of the wave. If we know the frequency and we know the wavelength, we can get the speed of the wave. Now let's switch over a little bit to the particle theory of light. And there's a really nice article on the Nobel Prize website that I have a link for on the website. and it talks about that duality. It's rather long, but it's a very good article. And when we talk about the particle theory of light, we're talking about photons. I'm sure everybody's heard of a photon of light, but a photon is a quantum of excitation of the quantized electromagnetic field and is one of the elementary particles. So basically it's a bit of light that goes by. It's a quantum of energy that goes by. What Einstein would think of when he looked at light is he looked at the wave, but on the wave there was a little denser part of the wave. There's a little knob on the wave that was the photon. And when we get more into some of this, we'll talk about the how Einstein got his Nobel Prize in physics, and that's part of where the photon came from. But now we have to look also in the particle theory of light is Max Planck and the Planck equation. And the E is energy again. The H is a constant. You're going to come across a lot of constants in physics. And there's two of them for this depending upon how we're measuring it. And F is frequency, just like we talked about frequency of the wave. An alternative to that, HF, is when we look at what Einstein did, and he took the Planck's constant again, times the speed of light, divided by the wavelength of light. And if you look back at the wave equation, you can see solving for F, you can get the speed of light divided by the velocity of light divided by the wavelength of light. And H has two different values depending upon if we're using joules or we're using electron volts. If we're using joules for the measure of energy, we're going to use 6.626 times 10 to the negative 34th joule seconds as our Planck's constant, H. If we need to use electron volts, we're going to use the H as 4.136 times 10 to the negative 15th electron volt seconds. And so you have to look and see what information I give you to see if you're going to use joules or if you're going to use electron volts. If I don't specify, it really doesn't matter. Joules or electron volts give me the same number, just a different form of that number. And I think that is it for this podcast. There's some other things about the discovery of X-rays that I have some articles that you should read. There's a video on swallowing that uses a fluoroscope that's kind of interesting to see the swallowing. And there's a good history of X-rays can be found at one of the links on the website.